welcome to this Agilent Technologies recorded webcast. We hope you find this webcast both interesting and valuable. If after viewing this recording you're interested in more, go to Agilent TM Webcast YouTube channel for more recordings, or sign up for one of our upcoming live sessions at www.agilent.com/find/web_seminars. Now, over to the presenter.
Okay, welcome and thank you for joining. I want to use this time today to look at some applications of really one of the most basic fiber optic measurement instruments, the optical power meter, which is quite powerful when combined with fast data logging. And we'll do that to look at these transient optical powers. So all through today, we'll be looking at a lot of graphs that basically look like this. We've got an optical signal where we're looking at the power changing over time. So like you probably recognize, this is very similar to a very common piece of bench equipment, the oscilloscope, and we're really getting similar functionality and use out of it as in the case of looking for optical signals. So today we'll be talking about being able to look at three main areas. In the one case, the stability of an optical signal, how it changes with time, and in particular how unexpected or unwanted events influence it. On the other hand, looking at the behavior of components that are supposed to somehow change the signal, for instance, switches. We'll talk about a few variations of out of this area. And finally, real transient responses, for instance, when the load into a component, in this case optical amplifiers, is changed, and how the gain changes, tries to regulate itself back, and there's a short-term change that we would call a transient. So we'll get into that at the end. Okay, and just as an indication, on the one hand, these are kind of useful general tests for any kind of diagnostics that you might have to take care of in your work. For the case of specifying components used in telecommunications networks, there are some standards that also refer to these kind of measurements. So these are three that I think are most prominent. One is really for transient losses, looking at kind of slow changes. They refer to sampling at 2 kilohertz in order to be able to pick up changes from mechanical movements, primarily when fibers get bent while during a maintenance operation. And these are used, for instance, for checking how good a fiber handling and storage system protects active fibers while a new fiber is installed or redirected, typical maintenance operations. Okay, another is standard for measuring just how fast a switch switches, switching time, bounce time until it stabilizes. We'll take a look at that. And this is probably a more or increasingly relevant, let's say, kind of measurement now when we talk about agile networks that can switch wavelengths to change bandwidth from one path to another with wavelength selective switches, other kinds of ROADM technology, and we can support those kind of measurements, especially in a multi-channel setup. Okay, and finally, these are standards recently or currently in development for measuring the kind of transient changes in gain for smart amplifiers that are designed to keep signals as constant as possible while other signals are being added or dropped, exactly because of this kind of wavelength switching that goes on in the wavelength reconfigurable networks. Okay, in these standards, a lot of them have been around for 10 years or more, and they've generally show a setup that has something that looks about like this, where there's a detector, an optical electrical converter, and that's to make an electrical time-dependent signal from the optical signal, and then that's detected with an oscilloscope. And really, we're getting into this today because with faster and more developed power meters, a lot of this functionality is available in the required bandwidths with a straightforward product, and that's the kind of instrument we're really supporting here today. So at that point, I'll get in my commercial for today. Most of these measurements today are made on this new set of what we call multiport optical power meters. We have a 4-port and an 8-port version, and the critical features for these are the very high sample rate that's adjustable with averaging times from down to 1 microsecond and up to 10 seconds, and being able to take per channel up to 1 million data points, and that's 100% buffered, so that we'll get into that, what additional functionality that brings us. To take advantage of that, we're using faster data transfer in addition to the traditional GPIB, also USB and LAN interfaces. And yeah, these are some of the typical data rates for getting 100,000 samples from 8 channels over USB 2. That takes about 1.2 seconds, something like that, for 800K samples. Looked at another way, we can get about 500,000 samples per second off of the unit, rather independent of the number of channels. Okay, and this has the ability, you can think of it as streaming data transfer or repeated logging, that while data is being measured, it can also be uploaded in chunks. Basically, you can measure 1,000 or 1 million points and upload them while others are being measured, and that makes it possible to pretty much continuously monitor a signal. All right, flexible triggering, some ways that this data can be then synchronized with your setup with electrical TTL signals with software triggering. Okay. And the kind of functionality we're using to make these measurements is we've had it in our power meters in the past, and this is really just an extension, so it's pretty much code compatible with the instruments that predate it. Basically, a logging measurement amounts to choosing a certain number of points and a certain averaging time, and then choosing to have those all measured directly right after another with self-triggering, or wait for hardware triggers for either to start the complete set of samples or 1 trigger per sample. And that's available again up to 1 megahertz sampling. What's new and that we haven't had before is this repeated logging capability, and that's done by splitting up the memory space for each channel into 2 buffers, buffer A and buffer B, we would call it. And while the detector is sending its power measurements, those samples are being gathered here, for instance, into buffer B. The previous measurements that were made on buffer A can be uploaded with essentially a single Skippy command and uploaded to the controlling computer. And that's what gives us the ability to do long-term logging of large amounts of data. Okay, here's an example of exactly that, and this is the kind of graph basically the sample software that I was using to make these measurements. So what you're seeing here is like what would come on a strip chart recorder. We're in the 14th second now of a chosen 30 repetitions, with each repetition 2,000 points of 500 microseconds. So each repetition was a second. Each second we get a load of data up to the computer, and okay, that can be set up with the software to scroll or store it, to filter it for events. In this case, what we're looking at is just the background light from fluorescent lighting. So if you had this unit on LAN somewhere, you could check and see whether your power meter is now in a continent with 60 hertz or with 50 hertz electrical power. Okay, let's see, what else have we got here? This is just a window showing how much of this data is shown on the screen. But this is the functionality that's achieved with repeated logging. And now we get into the examples of where we could use that and also use the single logging. These examples, again, I would group like we showed them before. One would be stability and the detection of disruptive events where you don't know when it's going to happen. So it means that's really the typical case of needing this continuous monitoring so that a signal can be watched for a long time until something happens, and then that data can be captured. Another case is where we have control of the time when there's something happening, like controlling a switch, like modulating a signal. And there we can, usually with software, make sure that the logging of power takes place at the corresponding time. And finally, the EDFA transient testing that I mentioned. So first, this testing according to the IEC 61300-3-28, that's looking for transient losses due to fiber handling. And a setup for that would have a stable light source applied to as many fibers as need to be monitored for this, and then most likely software to do this repeated logging for continuous monitoring, and simply watch the power as long as nothing happens, probably discard or decimate the data to a smaller amount that needs to be stored. And when something happens, in post-processing the computer detects, okay, it's moved beyond a certain threshold, maybe half a dB, then it will record that data, potentially with pre-trigger and post-trigger data, and store that, can label it as an event, and that can be characterized afterwards. When might that happen? Could be that somebody is, that's tested while someone is changing the configuration of other fibers in the system. It might also be a test for what goes on during temperature cycling of a link, and especially the connectors. Okay, I think we've pretty much gone through essentially what can happen there. For instance, with a connector, you could have the case of pistoning when the temperature changes, having the two ferrules of a connector pull back or away from each other a little bit and create a gap in the fiber connection, and then produce a drop in power. And then typically if fibers are bent, that's going to cause some increase in the attenuation of the fiber. That's what that can look like. This is just watching the power through a fiber where I pushed up against the strain relief where the fiber goes into the component. And okay, you can see this is something that's taken place over a couple tenths of a second in that case. That's kind of a typical event for fiber bending. And we're just seeing the power go down. The two things that people look for are how big is the transient, and then whether there's any residual loss afterwards. Has the device or system been permanently changed due to this? This measurement, just to get used to looking at this again, is shown on a dBm scale. We've chosen a certain power range for the measurements. 0 dBm was enough to capture these signals. They're about -6 dBm, sampling at 100 microseconds and taking 100,000 points. Okay, if we want to look at how stable that system is, one of the things we have to know about is how stable are the sources we're using to test them. And in other cases, maybe what we really want to test is the stability of lasers. So that's obviously something else we can do, and there's a couple considerations to consider when making that kind of measurement. And the first is strictly an issue of coherence. If we have a laser, and especially a single mode laser like a DFB, they can have a substantial coherence length, maybe typically 10 meters or so. And so if there are multiple reflections in the optical path, then you can get a reflective cavity where part of the beam goes directly through, but part is reflected at one point, reflected a second time, and comes back in. And so you've got a constructed, or you have an interference of light coming from two possible paths or multiple paths into the power meter. And depending on the path length, that can be constructive or destructive interference. Very often that changes quickly with temperature or any other movement or disruption of the fiber, and so it makes an unstable signal level. So here is a typical example of what could happen. All we've got here is an open fiber connection at the power meter. That's pretty typical. Usually a power meter, our power meters don't make physical contact to the fiber, but instead the fiber just ends here. And if it has a straight polish connector, that's about 3.5% reflection, 14.8 dB, whatever. That amount of light is going to come back this way. The DFB source in this case is isolated. That shouldn't really give us any trouble. We have an angled connector here, but we put a straight connection, and actually a fairly good one, in at this point, and that can reflect maybe a 40 dB return loss. And here's the kind of thing we see as a result, just looking at over a 10-second time period how much the power has changed. What we're showing here is dB. That's 11 millidB, so 0.01 dB. Kind of peak to peak, we've got 0.02 dB. We want to avoid that, and that's a good idea. Then one of the things to do is try to reduce the coherence length so that it's shorter than this pathing difference. And if a patch cord, typical patch cords for these kind of things are maybe 2 meters long, so that's the kind of range we'd like to get the coherence length shorter than. Okay, this was one of our DFB instruments. It has a function called Coherence Control. It puts a modulation on the laser current that's fast, so that for the averaging times we're using, the power of the DFB is stable. But there's a modulation like a chirp of the frequency or wavelength of the laser during that time, and that gives it an effective line width broadening and shortens the coherence length. And you can see as soon as that's turned on, this same setup was stable to less than 1,000th of a dB. The other thing you can do, of course, is try to avoid unnecessary connections. So here we're just going from basically the first patch cord without a second attached to it. So we still have a reflection here, but no source of additional strong reflection. And already that was good enough to give us about 0.004 dB stability, peak-to-peak stability. And this kind of brings us to the second case of what could be a source of instability in a signal, which is polarization. These are polarized light sources. We're going through single-mode fiber, which means the state of polarization along the length of the fiber can change generally fairly slowly, but it can evolve as the fiber moves. If there's any vibrations in the room, air movement, temperature change, that all can cause usually small but gradual changes in the polarization. But sometimes it's more rapid if there's really vibrations going on. And if the polarization changes, then the question is, how good does the power meter keep showing the same amount of power? So one of the typical specifications for fiber optic power meters, or for optical power meters in general, is their polarization dependence. These power meters are quite good. The typical polarization dependence is 0.01 dB, but you can see if we would change, if this fiber was moved around enough to change the state of polarization significantly, we would see even a larger, or at least according to our specifications, it would be allowed to cause a larger change than we're actually seeing over this 10-second time period. Okay, that was the first case of looking at stability and unexpected events. Now I'd like to go into what kind of tests we can make on devices we can control. Most of the measurements here, we're actually looking at our own instruments. This multiport power meter is turning out into a pretty valuable instrument for our own development, for being able to see what's going on in the instruments while we're developing them. So it's nice. This 1 microsecond time scale is quite useful for a lot of signals. Okay, most of these are, we don't need to do the repeated logging. We're going to do a single logging. We can make the event happen within a million points. So if we even use 1 microsecond sampling, we can still get a second or even 2 seconds if we use 2 buffers of the data that we're logging. So that's usually the way we're doing these measurements. And we can start it either from the computer controlling the device that we're looking at and making sure that we're logging during the time that that happens, or the device could give its own trigger to start the logging of from the power meter. Okay, and again, we want to have stable light sources if these are passive components that are just passing signal through them. One more point I'd like to mention: we do offer on request this kind of power meter also with electrical inputs, and that can be interesting in some cases for looking at how the optical signal changes with a direct time reference based on an electrical control signal, for instance. These are current meters actually and can be used to monitor photodiodes. Okay, so here's the one case. This is looking at a 1x4 switch. We're just monitoring all 4 outputs of a switch where we have a DFB signal at the input. We start the logging, allow the switch to change from one port to another, and watch what happens on all 4 ports. And that's kind of interesting for some kinds of switches. Here what you can see is the signal is on this, call it the first channel, which is blue on this trace. It's probably a little hard to see on the resolution. I hope not too bad. And at the time of the event, the light switches away from that port. This would be the fall time of that switch. It picks up into the new port where the signal is being sent. Interestingly, in this particular case, it crosses over one of the other ports, so there's a transient signal on that port that's fairly brief. And then finally, once we get into the new case, there's some ringing that goes on as this is now shown on a 1 microsecond time scale, and it decays pretty fast, but that was a ringing event that we could show using this kind of measurement. So if you like, that would be the switching time and the bounce that we would detect on that kind of device. Another case where we can see something about what these measurements can show is shutter testing. Our attenuator modules have shutters. They're mechanical blocks, so they really eliminate the light, except for any potential stray light. That's what we would have to consider, and this is a way to test how that works. So first of all, this is a test. Okay, I'm using 10 microsecond averaging time, measuring long enough to probably over 10 seconds, I guess, and we're measuring in units of watts. So this is a linear time scale. So we could first look at what the fall time of this shutter is. That turns out to be from the markers about 0.4 milliseconds. That's how fast it's taking for this shutter to cross basically the free space path of the light beam going between the input and the output of the attenuator. A faster case that we could look at is just turning off the light source itself. This is a DFB light source, the same setup, and I'm just, instead of closing the shutter, I'm turning off the DFB. In that case, you can see it's very fast. It's less than 3 seconds probably. I mean, at this point, we're really getting into the bandwidth limitation of the optical power meter, which is set up so that 1 microsecond sampling doesn't give undersampling for the bandwidth that we're using. And now if we look at this from the point of view of how good is the extinction of the shutter, then we'd like to look at that on a dB scale so that we can see how low the signal really gets when the shutter is closed. And so that's what this is looking at. Here you can see again the 10 dB drop, so losing 90% of our signal is again taking place in 0.4 milliseconds, and this signal is dropping down now from 0 dBm down to below -50. We're getting down in about 55 dB of measurement range here before the signal becomes kind of noisy, and that basically amounts to, well, it's displaying the kind of dynamic range we have when making this measurement. And like we'll show, the dynamic range, of course, depends on the averaging time we use. Shorter averaging times have a higher noise level, so we would have a hard time measuring down at this low power level. Another thing that's important is establishing the 0 power level in that case. And so for making this kind of measurement, it's important to use the power meter zeroing. Basically, that's just a case of making sure there's no light, 0 light on the power meter by applying, putting some kind of darkening elements in front of the power meter to block it, turning off the light sources. And it measures the electrical signal still coming from the power meter, and that establishes the 0 level. Okay. Here's now a case, same thing with a faster measurement time, trying to look at what's happening. So now we're at 10 microseconds, and here the noise picks up already about at the once we get beyond about -40 dB. Got a couple of funny points here. These are just how my software was handling underflow points. Those are points where actually the power meter is giving a negative value because due to the noise, it's actually got a signal lower than what the zeroing level has defined as 0 power. So there's nicer ways to handle that. I'll show that later. But that's kind of the effect. The faster you measure, you start to give up the dynamic range of the measurement. So that's a compromise to make in setting up these kind of measurements. Okay, just one more case, a millisecond for looking at the extension. Now we're getting down even below 60 dB range. And with in this case, we're using a 0 dBm power range, which we try to optimize. This can be changed in steps of 10 dB, and actually we would be able to measure probably another 3 or 4 dB above the top, so that kind of gives an idea of what the dynamic range is of the power meter in different settings. Okay, this is looking at now the time development of an attenuator itself. This is one of our new attenuators that has very fast setting, and it's actually a multiple channel element, so there's 2 attenuators in here. There's just 2 sources, 2 attenuators, 2 power meters. One of the attenuators is set to ramp at 100 dB per second, and the other one at 1000 dB per second. They can be programmed that way. We're just going to change the power between 0 dBm and -30 dBm. That's actually, we're setting the power because these attenuators have power monitoring and can be calibrated so that instead of choosing an attenuation, you can just choose the power level. So that's quite useful for receiver sensitivity testing, for instance. Okay, and in some cases you don't want that power to change too quickly, or you would like to follow some kind of ramp. So this gives us a way to look at how that happens. And you can see these are both just getting the same command at the same time to go from 0 to 30, but one has been programmed to go faster than the other, and that's what we're showing here. Okay, a few more on-off kind of measurements to show. This is the case of measuring DFB that's being directly modulated just by turning on the laser current on and off. And it's a 50% duty cycle. Part of what I want to show here is the fact that we're, in this case, triggering with the DFB. So the DFB has its own clock, and it's putting out a trigger, and we've programmed the power meter to start the logging. And so it starts the whole set of, in this case, 1,000 measurement points when it receives the first trigger after it's been armed. And this allows it to synchronize the modulation of what's being tested with the time scale. So you can see that works pretty well. The signal goes on right at the even numbers, 0.1 millisecond, 0.2 millisecond. The DFB was going at 10 kilohertz, and this is our 1 microsecond averaging time. So this is the case. Even with 1 microsecond averaging time, we're getting down past 30 dB. Well, even more than that, actually, close to 40, because we're starting out at, in this case, at a power above, well, fairly close to 10 dBm, actually. All right, but at some point, it kind of turns into the noise. So I would even correct that to be more about 40 dB. All right. Here's the same kind of measurement. Now we're just changing the time scale. Everything's slowed down, so the DFB modulation is at 1 kilohertz. Averaging time increased to 10 microseconds, another 1,000 points. Everything looks the same, but we do get farther down. Now the dynamic range, or the noise level, essentially, of the power meter is lower, and we can see this kind of detail better. That's what we're looking at. And then the next case is when we just go another factor of 10. Okay. At this point, you can see the noise is no longer a factor. We're just reaching the limit. Either the DFB is not going down any farther, or, and I think that's actually the case, that our bandwidth for the power meter is scaling with the averaging time. So as we slow this down, that also slows down. And you can see that this shape pretty much stayed the same as we changed over a scale of, or a factor of 100 in time scale. So I think the DFB is not doing that. I think that's just the scaling of the bandwidth of the power meter. Okay, so that's kind of the exercise looking at how we can deliberately changing signals and being able to monitor that on one or more channel with the power meter. And now I'd like to get into our final case, which is looking at EDFA transients. And like I mentioned, there's a couple of documents being worked on for standardizing this. One is called a two-wavelength method. That's what we'll look at here. And basically here the idea is that you have one or more signals that are going to be considered your steady state for the amplifier that you're trying to test. Those are staying on, and you would like to see them stay as stable as possible, while another signal or signals are added or dropped from the input to the optical amplifier. Another way to do this is to use a broadband source, and that would be the second document, and then change one of the wavelengths. And you can, one of the key points of the test is you would like to be able to change the relative power between the existing wavelengths or surviving wavelengths, they get called, and the probe that you're going to add or drop. If they're equal power with each other, it's like dropping half of your channels. Maybe you also want to check, okay, what happens if you only drop 1 of 10, basically, and then you could do that kind of test by making this one 10 dB stronger than this one. Okay, so the setup is again using this multiple port attenuator to control the output power of the two DFBs. They're multiplexed together with a wavelength-dependent multiplexer and applied to the EDFA. And then what you want to do is be able to look at the time dependence of just this signal. And to do that, you need to filter it with the wavelength. So generally here would be some kind of wavelength filter. That's, if it's tunable filter, then you've got some flexibility for choosing this one, or using a tunable laser here and testing at different wavelengths. Here I used our optical spectrum analyzer that has a filter mode to do that. So this is basically being used as a tunable optical filter. After the monochromator of the spectrum analyzer, the chosen channel is relaunched into a single mode fiber, and we can take that from the front panel of the OSA and then apply it to a power meter. Another way to do this would be to use a passive element, just a fixed wavelength filter or demultiplexer, and choose different wavelengths to apply to one or more power meters. Okay, so we're going to look at that and look at the time dependence of these channels. And if we look first at what do we see with an optical spectrum analyzer when we do this, the black line is the case, represents the case. Now we're looking on here with power in dB versus wavelength, and we see these two channels that are applied to the optical spectrum analyzer at the input. They've got, hard to see at this point, but they're about the same power level, about 11.8 dBm in that case. And what happens when we turn off one of them? Okay, obviously in that case it's the green channel. That one drops down, it's not there anymore. And the surviving channel, the black one in that case, gets, am I saying that right? No. It's the black, I'm sorry. It's the right one that is going to go away here, and the left channel gets stronger, and actually it gets almost 3 dB stronger because it takes up most of the available power from the EDFA, since we're driving it in saturation in this case. Also, the spontaneous emission from the EDFA goes up if the input load goes down. So that's what we're seeing here. This is just a simple erbium amplifier. There's no attempt being made here to regulate the pump power or to in any way remove transients or stabilize the signal. It's free running. What we're looking at here is what are the causes of what can become the transients. Okay, now what we're going to do is change to filter mode. That means we're going to choose one channel. In that case, we've chosen the right one, and that's going to be applied to this power meter. And this is the kind of thing that happens, exactly what we were seeing, that the other channel gets dropped, and when that happens, this power goes up. The rise time that we see for this channel is about 0.3 milliseconds, which turns out to be faster than what our attenuator shutter was. We were looking at that. So in this, well, in fact, we looked at it for a faster shutter. So in this case, we've done this by turning off this DFB with the disabling, which took place in microseconds. So we're really looking at the time scale of the EDFA. And you can see this is the kind of thing that, to first order, the smart amplifiers want to eliminate, is the change in static power when the number of input channels is changed. So again, if we this is just being done manually with now I'm using the shutter just for convenience. First dropping a channel, it goes up, adding the channel, it comes back down. And this is now on shown on a dBm scale. Okay, that's just a simple EDFA. This is not what people are looking for in this transient document, because it's really just a permanent or residual change. To simulate that, because the EDFA, which I've been using this word all along, EDFA means erbium doped fiber amplifier. It's one of the kinds of optical amplifiers and can amplify all of these wavelengths within a certain band all at the same time. I'm just using a simple one that really doesn't correct for itself. So to simulate correcting for it, I've put in another power control attenuator after the EDFA. These are not designed to change so fast that they can really compensate for that, but you can see the kind of effect here. So the power from the EDFA goes up. The attenuator detects that and increases the attenuation to bring it back to the chosen output power level. And this is what we call a gain overshoot in these transient measurements. And the same thing happens again going the other way. In this case, it's because this is being done with a shutter. The shutter was slower going in this direction for the add, and so the transient is slower, and the EDFA, or I'm sorry, the attenuator is able to compensate and catch it faster, so it doesn't go as far. So that's the gain undershoot. So that's basically the kind of event that we're able to look at with this kind of setup, and that would be the relevant test for a more sophisticated amplifier designed to compensate and eliminate these as much as possible. Okay. That's really all the examples I wanted to go through today. For more information, we've provided some links here. You can look at find more data on these power meters on the web. We do have an application note describing this logging functionality and how to program these power meters for this kind of measurements. Another thing you might be interested in is the standards themselves. They're available from the IEC. And finally, to get kind of an overview of our portfolio of fiber optic measurements, you could check here.
Thank you for watching this Agilent Technologies webcast. For more recorded webcasts, subscribe to our Agilent TM webcast YouTube channel. All of our webcasts are held live. Interact with our Agilent experts in the live Q&A sessions and gain access to Agilent materials. To view our upcoming live webcasts and to sign up for free, go to our website, www.agilent.com/find/web_seminar.